To show the function of the MP750511, I will use these circuits. This has two approaches: the discrete one with a hard implemented cutoff frequency, and the integrated one. In this case, I have a programmable device in case of our system evolves and other kind of frequency is required to the usage of our mixed signal system. In this case, I am using the MCP op-amp series and the MAX270 to reprogram the cutoff frequency. So, let's do it. Before to start, remember a fact. The function generator or waveform generator has a specific impedance in the output. In this case, 50 ohms. So, if your circuit or your test circuit device under test does not meet this impedance, you could use the utility menu, the option channel 1 to set, and the channel 1 load or channel 2 load according to the channel to use. You could configure a high impedance or a 50 ohm impedance. So you could try to use your instrument with your device using this configuration of impedance. So if you doesn't meet these requirements, you could see a key effect in the signal. You could send a 1 volt peak-to-peak signal, and your scope or visualization instrument could see a double of this magnitude. So, to avoid this effect, you could configure the impedance of your waveform generator. So, I configured this discrete model op-amp filter to 4.8 kHz of cutoff frequency. And our theory said to us that in this specific frequency, the low-pass filter has an integrator behavior. So if you have a constant, in this case a square wave has a constant 1, has a constant 0, and so on and so forth, the integrate is a linear equation of mt plus b function. So you see a constant in the square wave, so at the output you will see a linear or quasi-linear output, in this case a sawtooth signal. You can configure this signal to test this theory, so I will use a sawtooth or triangle wave, and the integral of a linear equation is a quadratic equation. So in the output you will see an effect of sinusoidal output, but this is not real. Why? if you have a linear section, you will have a square section. So rising square, falling square, falling square, rising square, so on and so forth, and it seems like a sinusoidal wave. But this occurs only in a viable or viable effect or visualization in the cutoff frequency. So if you modify this frequency, okay, you will see that the magnitude is falling each increase of the frequency. So if you follow the frequency, you will see that this magnitude, okay, recovers the amplitude. I will go to the square wave again, and you can see that the behavior is no longer a linear equation. Is the load and discharge, charge and discharge of a capacitor. Okay, I will go down more, and you can see this effect more evident. So that is not an integrator anymore. This occurs in the following kind of signal, in this case a triangle signal. So we have this kind of problems if we doesn't meet the frequency over the cutoff frequency. Okay, you could use the mode sweep of the signal. I will go from the 90 hertz, 900 hertz to the let me see, okay, 10 kilohertz. Okay, 10 kilohertz in a time of 10 seconds. Okay, as you can see, the behavior here, step by step in this sweep process, will recover the integrator behavior. So I will modify the start frequency from the 1 kilohertz to the 5 kilohertz. Okay, 5 kilohertz. In this case, I will use 5 seconds. Okay, here 5 seconds, and I will increase. Okay, take a look again in the square wave. We start with the charge and discharge behavior, but if the frequency increases, this behavior disappears and the circuit starts to function as an integrator. So a constant, the integration of this constant is a linear equation, and if we have a linear equation, the integral of that is a square equation. So this synthesizes a kind of sinusoidal signal. So let's take a look in the integrated approach with the programmable filter.